Okay, cloud person, thank you. All right, so good morning. Hope you had a great week. Today, we will go over primarily the AHA alarm, but I intend to finish up the stuff that I didn't last meeting on Tuesday. Before we begin, some administrative bits. The reading has not changed, due by February 8th in the Design Thinking book, section 1.1, which is pages 12 through 35. And project 3, the AHA alarm, is due this Tuesday on the 8th at the usual 11:59 and 59 seconds. Any questions about this? No? All right. So I always like to kind of wake up the brain a little bit, right? A little bit of a pleasant diversion. And this one is riddles, a riddle that my daughter, who's 9, particularly likes. So riddle me this. We have two people that you bump into or in the campus center, and this person is enjoying a cup of coffee with another person. And you've never seen this other person before that your friend is hanging out with. And you ask, hey, who's this? Who's this person? And so the answer this person gives you, brothers and sisters, I have none, but this man's father is my father's son. So my question, what is their relationship? Yeah. Pardon? Brothers and sisters, I have none, but this man's father is my father's son. A father and who? Okay. So anyone? So Caleb, right? Caleb says the father. So who's the other person? Father and who? Yes. And cousin, good answer. Good answer. No. Brothers and sisters, I have none. But this man's father is my father's son. You getting close? Close. Anyone else? No? Yes. Almost. Brothers and sisters, I have none. But this man's father is my father's son. It's a father and son, right? Because this man's father is my father's son, right? Okay, good. All right. Anyways, so where we last left off, get the brain juices flowing, we talked about a number of things, in particular persona, and we said it was a kind of caricature or sketch that captures the essence of different cohorts among the set of cohorts for whom you are developing a solution. And we said this helps you build empathy, and how you do this is based on data when you construct these caricatures, and that data is obtained from a so-called community survey. And there are a number of issues, trade-offs, pros and cons that we had discussed with something that might be in person or online, and various other important things like IRB. We also talked about digital input in contrast to digital output, and they say challenges come in threes. All right, there we go. And we talked about digital input in contrast to digital output, and we did that from the perspective of key parts of your program. The top part we call the preprocessor part of your program, the declaration of global variables. We had the setup and loop entry points. And in the setup, we said we set our pin, our IO pin, to be input. So it's going to read data. And then in the loop, we do a digital read and take some action based on whether it's a high or low. Okay, any questions about any of this stuff? No? And so today we're going to use digital read, digital input rather, in conjunction with the digital output, in a sense, think act cycle, structured as a finite state machine. That's two. Structured as a finite state machine. Nope. This thing has a little break in it probably. Let me try to unplug and replug and hope that does the trick. Okay. Yeah. You know, kind of animate it to music. This is not what I envisioned. So there's like a little bit of a connectivity issue physically. We need a new interface cable. Let me try the other side to see if maybe that positioning will put it at just the right angle to get a steady IO connection. Okay, synchronizing. This was unplanned. It's trying to find the device. Oh, my screen went blank. Let's say HDMI. Come on. Okay. Let's see. All right, let's try it. Let's try it on the other side again. Come on, you can do it. Computer. If you've ever seen the Star Trek movie. Nope. All right, this is not good. Let me flip this over. I apologize for this technical difficulty. I am equally as surprised as you are. Come on. Nuts. This is not good. All right, so let me just shut that off. Back on. There we go. All right. So I won't go near this thing because I think the vibration is kind of disturbing the cord. I'm going to submit a ticket for this. All right. So we talked about two input and output. I said, any questions, pin mode, blah, blah, blah. Okay. All right. Any questions about all of that? No? All right. So where we left off, we started to talk about the passive buzzer. And specifically, we introduced this idea of a square wave where we're alternating the amount of time, delta t, that the signal was high going to the right, you're right, that's time, at 5 volts versus signal being low at 0 volts. And so we said the percentage of time that the signal is high, we call the duty cycle. And for some components, so-called integrators like a motor, this duty cycle is the same, varying this duty cycle is the same as varying the voltage to this device. And so the speaker uses this to generate the pressure waves, the buzzer, in order to play music and create sounds. And so let's pivot to the 5-minute group presentations that we talked about. And this is going to be in what I call engineering stand-up mode, which is an agile technique. And so each group is going to have a member talk for no more than 5 minutes, or if you choose members, plural. And for this exercise, everyone in a group who's not currently presenting verbally is going to have to listen intently, because you're going to have to find 2 points for constructive criticism. Now, in giving constructive criticism, rather, it's very, very important that you not be a monster, right? And because there are so many different personality types, if you're more of an INTJ or something, variation thereof, you're very direct and you want to just say that idea is silly, it's foolish. You want to make sure that you're not coming across as a monster. And for those who are more ENFP and more extrovert and feeling and things like that, you want to remember that nobody wakes up a monster. Nobody intends to be bad, mean, or what have you. So also don't take it personally. And so how we're going to meet in the middle is when you give this constructive feedback, If you need more detail about something, and please try to find something you'd like a little bit more detail on, and you're going to say something like, please help me to understand blank when you say blank, or something of that nature. And if you think somebody could have done a little better on something he or she has described, please adopt the posture. I think this is a great idea that deserves further exploration. I'm eager to hear blank about blank, right? And so again, you're not denigrating the person, you're discussing the idea that the person brought up, okay? All right, so let's have the first group. If a group doesn't stand up, I will just pick one. Okay, how about the back right? So the back right, yes, you have 5 minutes to give your verbal presentation, all right? It can be brief, and everyone else, and you're presenting to your colleagues in the class. You're not presenting to me, to your colleagues, right? So you have 5 minutes. I'm sorry? Yeah, you're gonna, however you choose to apportion it, you have a total of 5 minutes to go through your points. 5 minutes. And the clock starts now. 5 minutes, first group. That's 10 seconds. You can start. The back right-hand group. Yes. All right, you're talking to your colleagues, not to me. 24 seconds. Okay. I'm going to have to cut it off there. Any constructive feedback? Nobody? No? Yes. Okay. Good. Thank you. Thank you. Let's thank our speaker. All right, let's have this group in the front. You have 5 minutes. Start. Okay. What's that? So any constructive inputs for our group? Let's hear from somebody else. No constructive input. None? Okay. So you'd mentioned Morse code and lighting patterns. Um, Back in the day, I was in the amateur radio club as an undergrad, and one of the things you had to learn was Morse code. And Morse code is sometimes taught as auditory, and you don't just listen for the dots and the dashes. You kind of listen to it like a language, like a sound. And so, how would you integrate the auditory part with the lighting patterns? If you could expand on that, please. Yes, yes. And so you mentioned lighting pattern like Morse code, right? And Morse code is often taught um, using the audio sensor modality. And so how would you integrate, or maybe something I missed, you integrate this audio for the teaching purpose with the light pattern? Okay, all right. What's your intuition? Hmm. Hmm. Okay. Hmm. 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 Okay. 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 Good. Very good. Thank you. Let's thank our speaker. Now, one of the things that's really, really important, it's okay to not know, right? Don't be afraid to say, I don't know. This is my intuition and I can find out. So very good. Thank you. All right. So let's have the next group. Yes. You have 5 minutes and you can go. And you're talking to your colleagues, not to me. Okay, great. Thank you. Any uh, constructive feedback? No constructive feedback. None? Let's have somebody from the back. Constructive feedback. Okay, good. Thank you. Let's thank our speaker. Let's have the last group. Um, you have 5 minutes starting now. And you're talking to your colleagues, not to me. Great, thank you. Any feedback or constructive input for them? Let's have someone from this group. Any constructive feedback for them? Yes, yes, absolutely. All right, thank you. Let's thank our speakers. All right, good. And so this is expected to be difficult in the beginning, and some pointers that I'd like to impart on everybody is that you should also be aware of how nonverbal communication impacts the messaging, right? And so what you've just done is an agile technique. And typically when you do this in industry, you're in a room and there are no chairs, right? You don't want people to be comfortable and spend a long amount of time. And you have a small amount of time to give an update about where your subsystem or where your component is going with respect to all the other things in the team. So imagine you worked at Microsoft and you were on the Microsoft Office team, Office for Windows, and maybe your group was doing the grammar and spell check. Another group was doing the rendering, all of the drawing of fonts. Another group was doing perhaps the object integration, where you can embed a spreadsheet or a figure or something in a Microsoft Word document. And so what would happen is in your weekly engineering tag-up meetings, as they're called, you have a master schedule, and there's someone called a program manager who's tracking all of the schedules for all of the components that collectively comprise the product. And so when you give a check-in meeting, it's a quick engineering overview about what's happening and where things are going. And it's on purpose that it's a very short monologue, so to speak, by each team. And there are no chairs because they don't want you to sit there for 2 hours going on and on and on. And so when you communicate, of course, there are different personality types. Some who are extroverts are perhaps more well-tuned to public speaking off the cuff like that. And some who are introverts are probably feel like it takes a lot of energy to do that. And if you're an introvert, you're probably feeling exhausted, right? And so one of the things that's really important to remember is that you're not a tape recorder, right? You're not going to memorize some verbiage and then vomit it back out word for word. What is very helpful for these sort of exercises, these sort of activities, is to have a list of talking points, right? A set of bullet points, which are the pieces of information that you want your audience to walk away with. And you can use whatever words you want to get across those talking points. But the key, and you see, so for some people, it's very, very smooth and what have you. If they did it 10 different times, it would be 10 different ways they choose to say that, but you're addressing talking points. And so I want to break people out of the habit of feeling that you have to memorize and regurgitate the words you've memorized, right? You're addressing talking points, and we'll have ample opportunity throughout the course of the semester for this class to do that. The other thing with nonverbal communication is to find what I call pause points. And if you watch speeches given by people who are really, really good professional speakers, you'll notice they have a way to pause. They might say, let me think. That's a great question, while they're stalling for time to try to think of what a good answer might be. Now, find a way that's natural for you to give a professional pause. Moreover, when you have your body language and you talk about something really big, use some nonverbal gesture to note really big or really, really small, right? And some people, naturally, because of their background, they speak with their hands well. But for those who aren't practiced in that, it's something you have to make a deliberate effort at, right? And when you use your hands to speak, or you say, interesting, you're kind of giving a gesture to try to shape the nonverbal communication equally as much as the verbal communication. Because people remember really, really big versus really, really big. Or you say, I am so excited versus I'm really excited, right? And so it's really important to master these nonverbal gestures and to choose them appropriately in order to make your point about what it is you're trying to get across, okay? All right, in addition, if you're nervous about something, and this pointer was given to me by an executive from IBM, if you're nervous about something, don't hold a piece of paper. It's going to be very apparent that you're nervous. Choose something that's a little bit heavier. It could be, maybe it's your water bottle, post-COVID, of course, you can take a drink, you can pause, and a cup. is a really good prop to use when you're giving a talk if you're nervous, right? Because if you're nervous, you want to pick something up and pause. And even if you have no water in that cup, make sure it's an opaque cup. Don't have something that's a transparent plastic cup because people can see that there's no water in it. But you can have an opaque cup with nothing in it. And if you're nervous, go by, take a sip. But in your mind, you're going, ah, 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 feel better now, okay? And so there are absolutely lots and lots of tricks and techniques you can use to address any nervousness, to have pauses, and also to make your presentations go a lot more smoothly. Okay, any questions about that? Does that make sense? No questions? All right. So let's continue on, and we'll pick up with the stuff that we didn't finish last time. And I like to do a time check every so often. And that's about buzzers and tones. And so we talked about this idea of duty cycle, the relative proportion of time, delta t, for which the signal is high versus the signal being low. We also have this idea of frequency. Now, a frequency is the amount of times measured in hertz or cycles per second for which a waveform repeats itself. And so in this case, we start low, we go some amount of time, delta t at low, transition to high, delta t high, and go back to low again. So that is one so-called cycle. And so frequency talks about the number of cycles or repetitions per second. In this case, we have a 50% duty cycle. So delta t for low and delta t for high is the same. 50% of the time, this waveform is high. But you can see we have 3 cycles in 1 second of time. Imagine this for 1 second of time. We have 1 cycle, we have another cycle, and then we have that last cycle within that 1 second. We can double this from 3 hertz or cycles per second to 6 hertz or cycles per second. Mind you, the duty cycle is still 50%. That has not changed. That same delta t, albeit smaller, is still the same for the amount of time that the waveform is a 0 volts low and a 5 volts high. Okay, any questions? Does that make sense? And so we can see here, we have 1 cycle, 2 cycles, 3, 4, 5, and 6. So we have 6 cycles in that 1 second. And so with the buzzer, the passive buzzer, the number of cycles per second for which you turn it on and turn it off, that will cause the piezo crystal to push and to return back to rest, creating a pressure wave, which you perceive as sound. And so the more times per second it pushes and rests, the higher frequency you hear. The fewer times it pushes and comes to rest per second, it's a lower frequency sound. Okay. Any questions? No? And so, yes. Pushing, literally move, clicking, pushing air, like that. If I could do it fast enough, you'd feel a gush of air. And so if you go to the back room at Best Buy, right? Where they have all the really fancy speakers that cost a lot of money, and you kind of turn it to your favorite music or what have you, or bring your Bluetooth system or whatever, and you'll see the speaker physically move in and out. And so push literally to displace itself mechanically some distance. Okay, all right, thank you. Any other questions? And so this buzzer is an actuator. It converts a signal, that logic high and logic low for the waveform, into mechanical energy in the form of a pressure wave pushing the air molecules that you perceive as sound. And so again, we have our preprocessor section of our code. We have our setup and our loop entry points. We start our setup with turning on the serial system if you want to use print lines to the console. And then we set up the pin for the buzzer to be output, because we're going to go from signal to mechanical energy. It's an actuator. And then in the loop, we write our logic high to the buzzer, setting it to 5 volts. Then we delay some amount, and then we write a logic low to that pin for the buzzer, and we delay that same amount. And so when you have these 2 delays, the same amount, that implements a 50% duty cycle. But if the length of pause is small, that's going to be higher frequency. Okay. Any questions about this? No? All right. So, oh, I just said that. That's about 100 hertz, because 10 milliseconds goes into 1,000, which is 1 second, 1,000 milliseconds per second, about 100 times. So plus or minus, depending on your system, that's going to be about 100 hertz sound. Okay. Any questions? Yeah? All right. And so this can get pretty tedious if you want to do something like play music, which is what we'll do in this afternoon session with the AHA alarm. And so there's a library implemented called the tone library, and this is a snapshot of the Arduino language reference. And this tone library does it for you, right? So you start out, you have different APIs for tone. You give it the pin number, the digital IO pin, and then you give it the frequency in cycles per second. And if you do that, well, it'll generate it for you. It'll keep generating it until you turn off the tone. And the APIs tell you how to do that. You can also give it the second API version, or use the second version of the API, where you give it the pin, the frequency, and also the duration. If you do not give it a duration, it'll keep going until you explicitly turn it off. Now, of course, this kind of assignment, depending on how you react to sounds, can either be very pleasing or a little bit disconcerting, right? And so sometimes you might find yourself pulling the ground pin just to kind of turn this thing off. Yes, question. For this experiment, no. It's the same volume. But that's something that'll be coming, not necessarily for volume, but we'll introduce a potentiometer, a variable resistor, so you can kind of turn off, or even a switch, just click and break the circuit. Any other questions? No? All right. Okay, so let's look at the AHA alarm. And prior to executing the project, you should be asking yourselves as a group a bunch of questions. Well, what is an AHA alarm? That's a very important question. There's a bit of a backstory, some 80s pop culture. What components do I need? You want to collect your tool chain, your parts list, as well as tools like your breadboard and the jumpers and the Arduino board and the power cable, of course, that you're going to need to implement your project. How do you use the sensors? Well, I'm pulling away some of my support because I want you to get into the practice of looking up the data sheet for your components, right? And so this is from the Key Studio 48-in-1 sensor kit that is in your IoT kit. Now, this has a wiki-style documentation site and a PDF you can download, which is very extensive and tells you everything you need to know, including application notes or example code on how you use all the sensors and actuators that are in the kit. How you lay out your breadboard. That shouldn't be an accident. You should plan and design your circuit, not just jump straight to the execution. Exercise, please, these good practices while things are still simple before we start layering on more sensors, more interactions, networking, and all that good stuff. How do I generate a tone? In Arduino Sketch. So again, don't just jump to the implementation, try out the application notes, try it out and convince yourself that you understand how this works and how to use it, how to get certain behaviors that are desired out of these devices. Where do I put my pitches.h file? I'll allude to pitches.h a little bit later, but you will be defining symbols using the preprocessor to stand in place of the individual notes that you will then play from the Arduino, and all of that is in the documentation. Okay, so once you have a semblance of an answer to these questions, then you go ahead, do your tasking, which group members will do what, because it's efficient to do it in parallel. One group will do the hardware, maybe one group will do the software and the finite state machine design. So the backstory, in the 80s, a new medium, the music video, came onto the scene, and MTV, which used to show music videos at the time, was the pioneer in that. And it was the first time that you could put together the visuals, the video, special effects, along with the music. And it was a way for an artist to, in effect, get to know a little bit their audience, or the audience to get to know the artist. Because before, with music, it was primarily an audio only modality on the radio or in records and tapes, on CDs and DVDs, or with streaming now for all of you. You really didn't know who the artist was. You just knew the song and the vocals and the score. And so AHA introduced a very novel at the time approach of putting together animation, pencil sketch animation specifically, with live video. It had never been done before. So it was a pretty big advance. And so one of this group, AHA, which was the name, out of Norway, one of their hit songs was a song called Take On Me, and that's going to be the clips that you're going to play when you sense human presence with your circuit. Okay. So you're going to be coding this and structuring this computation as a finite state machine, but this finite state machine is going to implement the sense, think, act cycle. Mind you, for any good finite state machine design, like we talked about, you first design your algorithm, then you define your states. You create what we call a switch sandwich, a switch over those states. You wire in your transitions, focusing on the positive logic, add in your conditionals, and then your functions that implement the behaviors for each of your states. Now, in the project specification, the states must be sense, think, and act. And so those are going to be the cases using number defines, or you could have variable names if you want to do it that way, but your states have to be these three: sense, think, and act. But instead of implementing the behaviors directly in the case statements, you're going to be implementing these using callouts, using behavior routines or behavior functions. And so your sense function will return a byte called measure environment with no parameters. Your think function is going to return a Boolean, is going to be called isPerson, is a person detected, and is going to take as a parameter this measurement that was returned back from the sensing action or sensing behavior. And then your act routine is going to return void arguments, so it doesn't return anything, and it's going to be called sound alarm. And so you're going to call in each one of your case statements for the implementation, not one of these routines, and not implement those behaviors directly in the cases for the switch statement. Any questions? No? Does that make sense? Okay. And so we're putting on a little bit more abstraction because our circuit and our underlying system, our computation, is getting a little bit more complex. We're using both digital input and digital output, structuring it as a sense, think, act cycle. All right, so of course, you're going to prototype this on a breadboard. And this, I updated it a little bit earlier this morning because I thought it was interesting. I'll post this later this afternoon. A breadboard actually started out in the early prototyping days, going from something called wire wrap, which I won't talk about, to literally people were building their circuits on wooden bread cutting boards. Why? Because it was cheap and it was already there. And so these are some two examples. You can see someone literally built their circuit. And one of the things you'll see is they wrote in black magic marker the circuit diagram for each one of the components that they're laying out along the circuit. This one is a little bit more elegant. It's raised, but you need more stuff, right? You need some thicker wires and you need a bunch of nails. And people literally did this on physical breadboards, hence the name breadboard has persisted. Now, of course, the breadboard that you've come to know has two different types of conductive pathways. It has what I was calling the column, which are these, in this diagram or this figure, these left to right connections. And every pin within a column, or what I was calling a column, is sharing a conductive pathway. Then these edges that I call the positive rail and the negative rail, that's a single conductor extending the entire length of the board. Now, don't pull apart the breadboard. We only have limited parts. But if you were to pull apart the breadboard on the underside, you would actually see these strips of metal that coincide with the conductive pathways for your breadboard. Okay, any questions about this? No? All right. And so the ravine, gully, ditch, or whatever you want to call it, canyon, between the two halves of the breadboard are purposed with straddling certain types of components across it so that you can connect leads to them. More specifically, a chip in what's called DIP or dual inline Um, uh, I can't remember what P stands for. Brain hiccup. Dual inline package thing. There we go. Dual inline package format. It allows you to plug a chip into the breadboard, one row of pins of the DIP package on one side of the ravine, and the other row of pins on the DIP package on the other. And you notice each pin has its own conductive pathway. So now you can include chip circuits on a breadboard when you're doing your prototyping. And that's useful for lots and lots of applications. In this picture on the right, you'll see an LED that straddles the ravine. And so it's very useful when you have components that have an input and an output to straddle across the ravine. Okay, any questions? No? All right. And so this is an example circuit. And remembering what these pathways are in this diagram they found, they do a nice job. They mark in green what the conductive pathways are. And you can see the rails here. There's a positive rail here across, and they're using the ground plane, a negative rail across here. And we see a bunch of components, and it illustrates each column and what the conductive pathway looks like. And so it's really important to think ahead about your circuit. Don't make it arbitrary, especially when you have circuits that involve a lot of components. You're going to want to think about your layout ahead of time. Now, there are some pieces of software, which we don't have access to for free, that will help you in that layout, not just for breadboards, but more specifically for circuit boards, which you then send out to be manufactured, you drill through, and then you solder them on. But we're not going to do that kind of fabrication. For the sake of ease and for pedantic reasons, we're going to limit ourselves to breadboards. If time permits, maybe towards the end, we might get into soldering, but we have to check budget and all those good things. Now, in this circuit, one of the questions I'll ask you is what's the value of this resistor? We have orange, it's a 4-band resistor. We have orange, brown, and gold. And so let's think about what this value is. And so it's black, brown, red, orange, yellow, green, blue, violet, gray, white, right? So if we think about these color bands, what value is orange? Black, brown, orange. 3? 3. So we have 3, 3, and then that third band, the brown, is a multiplier, right? So black is a multiplier of 1. Brown is a multiplier of what? Of 10. So we have 3, 3 times 10 to the 1, or 330 ohms. What does this gold mean? That's our tolerance, right? We have gold, silver, and no color. Gold represents a 5% tolerance. And that tolerance is very important depending on the type of circuit you're trying to build. And if your circuit needs very precise voltages and currents, you want to pay more for a resistor that has a narrower tolerance. Okay? All right, any questions? No? All right. So let me ask you this. Where are the anodes for the LEDs? What is the anode for an LED? It's the, pardon? I can't hear you. The longer pin. But on the circuit diagram, you're correct. What does the longer pin represent in the circuit diagram? The positive voltage side, okay? Because it's important, as we said, our LED is like a one-way switch and, well, diode, but the light emitting part, this one-way switch also lights up. So it's a one-way light bulb. So it's really important that you know which leg is the anode and which is the cathode, and it's absolutely the longer leg. So if someone's assembling a circuit and they cut the legs on the component so that they're both the same length, then you have to try both ways, right? Okay, so what are these? Anyone want to venture to guess? What are these things? Yes. Mm-hmm. They are buttons. Yes, they're switches in particular. So if you press the button and hold it down, it's going to enable or complete the circuit or pathway. If you release it, it's usually spring tension, it's going to break the circuit or pathway. Now, these particular switches, when you're programming them, and we'll talk about it in a future assignment, you have to have what's called debounce logic. Because when you make that connection, you're literally taking two conductors that were not physically touching one another, and you're bringing them into contact. Now, that contact isn't always a smooth landing. There's a little bit of connection and disconnection in the beginning when they're close to one another, right? And so that's called bounce, because what ends up happening at a microscale level is you get a signal that goes low, high, for a brief period of time. And if you're going to read input of saying, is this circuit closed 0 volts, I'm sorry, 5 volts, or is that circuit open 0 volts? How do you read that input if your connection is bouncing? And you need something called a debounce algorithm, okay? All right, so we have our switches, we have our LEDs, we have our resistors, we have our power and ground. So what do you think the circuit does? What is the circuit? What does it do? Yes. You press the button and it turns on the bulb, the LED. Yes, yes. Okay. I know it's funny. You know, there's going to be a generation coming soon at which they won't know that an LED isn't the same as an incandescent bulb, because when they pivoted from incandescent to LED, now sort of through casual contact, you know, in the markets and stuff, you're going to be like, but that's a bulb. What are you talking about? You know, yeah. So it's going to be probably history books at some point. All right. Anyways, so let's take a look at our sensor package. And here we have the PIR motion sensor on the left, and we have the passive buzzer on the right. And these are the specific ones in the Key Studio kits, component kits that you have. And here, if you notice, the pins at the bottom are marked with a G, V, and S. G stands for ground, so that pin's going to get connected to ground on the Arduino. S stands for signal. That's what's going to be connected to the digital I/O pin. And lastly, V stands for voltage. Sometimes you'll see that described as VCC. Sometimes you'll have it described as V+. Sometimes it'll say 5+, meaning connected to a positive 5-volt source. There's no one standard for how they label the pins, but typically for sensors and actuators, you're going to have a ground connection and a voltage connection so that you can power the device, and then you're going to have a signal connection, a signal pin, so that you can send data to the device or read data from the device. And it's up to you as to which I/O pin you want to use. Okay, any questions? No? All right. And so if you look in the Key Studio documentation, which is pretty generous and very extensive, in my opinion, they'll give you an example wiring diagram. And in their diagrams, they assume you're using their product. Why would they have someone else's Arduino board when they make one, right? It's just good advertising. And so they're going to show you physically what the pinouts are. And typically, the standard in electronics that most people follow is that you use red for the color of your so-called hot wire. That's the wire that contains the positive voltage signal. And you use the black wire for ground. So immediately you can look at the circuit and say, aha, that's ground, and this is positive voltage. And then the signal wire in this diagram, they're using blue. You can use whatever color you want. And in similar, if you ever see a network closet in a data center, they often use colors to code different types of lines. It just helps you organize things a lot better. And so they also give you a specification, and they'll give you something like the voltage that it takes. And it's really, really important not to exceed the maximum. Because if you exceed the maximum, you're going to burn out your component, and you'll know. Oftentimes, you'll smell something that's almost like burning tires, if you've ever smelled burning tires. It's like a plasticky, strong smell. They'll also give you something about the amount of current this thing draws. This component, the PIR motion sensor, takes 15 microamps. So that's how much current it'll pull. And the reason why the input voltage and the current draw for the components are important is if you're building a system that consists of multiple devices, sensors and actuators, you want to compute something called a power budget. You want to know how much current will all these devices take, not just when they first start up, but when they're operating normally. as well as the voltage, because you want to make sure that whatever power source you're using to supply your system has enough power reserve, energy stored, charge stored, in order to power all the devices. So you take all the devices, you add up all the currents, you add up all the voltages, and you want to make sure your battery is bigger than that. And depending on how long you want it to run, it could be a little bit bigger or it could be a lot bigger. Okay. Any questions about this? Does that make sense? Now, we're not dealing with power budget now, but it's a consideration. They'll also talk about some of the operating characteristics, like the temperature range in which this will operate. That's pretty generous, negative 20 degrees to 85 degrees Celsius, right? You want to make sure you get the units right, because you don't want to deploy a device in an environment that is beyond the capabilities of your components, and that includes the processor as well as all of the sensors, right? The detection angle, the operating characteristics, this thing has a detection angle that's a 100-degree cone of detection from that sensor, and the detection distance up to 7 meters. Now, that's idealized. You might be a little different depending on the environment. Because this thing is triggered by heat gradients or moving heat, in a cooler room, it's going to work a little bit better than in a warm, humid room. And so when you see these characteristics, the question to ask yourself is, under what conditions do they compute this? And it's usually under idealized conditions. Okay. Any questions about this? No? All right. And so this is the basic circuit that they give you in the example manual for the Key Studio sensor kit. In this case, they're using the indicator built-in LED, which is pin 13 on the Arduino board. Their board is compatible, and they light up that indicator when this thing detects a warm body and also prints out a print message. And so here we have our indicator. It's going to be an output I/O pin. We have our sensor. It's going to be an input I/O pin. Then in our loop, we do a digital read. And here, they're storing as a local variable the state that they've read in. And they use that state, whether high or low, to set the indicator LED, right? They've chosen to do it that way. You can do it a different way if you choose. But what I really recommend is that you copy and paste the example code, tinker with it to convince yourself how that particular sensor works, okay? All right, any questions about this? No? All right. So there's the printout. And so this is what you'll see if you use the example code. This is the buzzer specification. I won't read those, I'll leave it up to you. But in the buzzer sample code, they have 2 while loops, or rather 2 for loops within a while. And you'll notice here, these have different numbers of iterations. That's gonna be the duration at which the buzzer will ring. And then you'll notice here, there's a different delay here versus down there. That's gonna control the frequency, how many cycles per second or hertz this thing is gonna push and let that buzzer element come to rest to control the frequency. And so I recommend that you experiment with this example code to tinker with the frequency before you use the tone library. Okay, any questions? No? All right. And so let's take a brief look. Are we till 11:45 or 11:40? 11:40, okay. So let me just wrap up with this. We talked about what a preprocessor does with your compiler for the board. And we're going to focus on this preprocessor. Before, we had number sign include and the name of a file in angle brackets. Well, when you use these angle braces with the name of the file, that's for a so-called system library header file. It's a bunch of definitions of functions as well as preprocessor macros, but these are system libraries. It knows where to go on your disk to fetch these files. Now, sometimes you'll see, instead of the angle brackets, you see quotation marks. Number sign include some name.h in quotations. That's for including your own header file. So you don't just have the ability to load system header files. You can create your own header files for functions and definitions that you write and include it in your programs. So taking a closer look, you're going to create a file called pitches.h, and you can create that in the Arduino IDE. But if you do that, you want to go back in through your file system and change the name from a .ino file, which is what the Arduino IDE saves text as to a .h file. That's really important because if it's not a .h file, well, it's a little bit messier if you try to include something that's not a .h file. You might get a complaint from the compiler. And so here we have number sign defines, and we have different notes, and we have these delays, which are going to translate to these different notes on the keyboard. Now, I played bass guitar in the jazz band in high school, but I wouldn't call myself a musician. If you want to tinker with the music, you're free to, but I recommend, please make sure you're completing the assignment first. And you can go crazy and do all sorts of creative stuff after you've completed the task. And so this will load the pitches.h file at the point where the number sign include for it occurs. And it's nothing more than reading the file into memory and doing a replacement of that number sign include command with the contents of that file. The last thing is you'll notice here this if not defined, pitches underscore h, and this end if, that's a conditional. And what this does, it says, does this symbol pitches underscore h exist in the preprocessor? If it does not, go ahead and define it. And that's what we do there. Now, this technique is a way of controlling your includes in your programs to make sure you only include it once. Because if you include it twice, the compiler will go crazy and say, I don't know what to do. I have this doubly defined. So that's just a little technique to use in your preprocessor includes. And so with that, we'll end there and we'll pick back up, 2 minutes over, darn it. We'll pick back up at 12 noon and we'll just do building then. All right, so I'll see you then. Enjoy your shortened break. Maybe we'll start 2 minutes later just to kind of make up for that. All right, let me stop the recording.